Let us discuss about encoding techniques. In data communication, an encoding technique is a method used to represent data in a specific signal format so that it can be transmitted over a communication medium and also it can be correctly interpreted by the receiver. It defines how bits, characters, or symbols are mapped to signal variations such as voltage levels, frequencies, phases, or even light pulses, depending on whether the transmission is digital or analog. We have various encoding techniques. First one is analog data to analog signals. That means, say, suppose you have information in analog form, like it can be voice, music, etc., and you want to send it as an analog signal over a medium. Say, here, let us take radio waves as a medium. In order to do that, you modify some property of a carrier wave based on your data, which is nothing but modulation. And these are some of the modulation techniques we use for converting this analog data to analog signals, that is amplitude modulation, frequency modulation, and phase modulation. Best example for this is FM radio stations send analog audio data as frequency modulated signals. And the second method is analog signal to digital data. Say, suppose you have a continuous time, continuous amplitude signal like voice picked up by a microphone, and you want to represent it in a binary form so that the computer can process or store it. This process is called as digitization, which is usually done in three steps. One is sampling, second one is quantization, and encoding. And the techniques which comes under this are pulse code modulation, then delta modulation. So pulse code modulation means sample the signal at fixed levels, then round off to a nearest level and then quantize in binary. Whereas delta modulation means store only the difference between the successive sample, which can sometimes gives better efficiency. Best example for this is when you record audio in a computer, the sound waves are digitized using this pulse code modulation. And the third method is digital data to analog signals. Say, suppose you have a binary data but want to send it over a medium that only supports analog transmission, like telephone lines or radio waves. You convert binary values into changes in a carrier wave, and that process is nothing but digital to analog modulation. And there are some of the modulation techniques like amplitude shift keying, frequency shift keying, and phase shift keying, which fall under this category. And the example for this is old dial-up internet used modems to convert this digital computer data into analog computer signals. And the fourth one is digital data to digital signals. Assume that you already have a binary data but need to represent it as a voltage pulse pattern for transmission over a digital medium like Ethernet cables. Here, this can be done, or this process nothing but line coding, where we are assuming or assigning voltage patterns for 1 and 0. And there are some of the methods like unipolar, bipolar, polar. So unipolar means single voltage level for 1, zero voltage for 0. Whereas polar means positive voltage when we get binary value 1 and negative voltage for binary value 0. Then bipolar is alternating positive and negative voltage for 1, whereas for 0 it will be 0 voltage only. Example is Ethernet uses the specific line coding schemes to transmit data as electrical pulses. Let us see how the analog signal is converted to digital data. So this is the analog signal, which is a smooth continuous wave. Looks like a sound wave from a microphone. Computers can't store or process this directly because they need numbers but not continuous curves like analog signal. So this will be sent to PCM encoder, and the first technique used in PCM encoder is sampling. So in this, we measure the signal's amplitude, which is nothing but height at regular time intervals. So usually will measure it regularly, for example, every 1 millisecond, and we capture its shape in a series of numbers. So this shape, it is captured in the form of time series or some series of numbers. So it will be something like this. We are capturing its shape in series. So let us imagine a bouncing ball. Say if you take a photo every half second, you don't see a smooth motion. You see the ball's position at those movements. For a signal, even we'll do the same. So take a snapshot at every or at equally spaced times. Write down the height, which is nothing but voltage of the wave at each snapshot. And in this PAM, each snapshot value becomes the height of the short pulse. The time spacing between the pulses is fixed, and the height of each pulse is proportional to the original signal's amplitude at that sampling moment. So, after sampling, this data will be provided to this quantizing. So, where each sampled value can be any height in theory, but we limit it to a set of fixed levels. So, we usually round off the number. Say, suppose here we considered height of the wave in multiple or in regular time intervals. Say, if you got the height between 5 and 6, like 5.4. So, this value it should be rounded off to nearest allowed level, that is 5 in case of this quantization. So here we'll just round off the decimal values into normal integers. This step turns the continuous sample values into discrete steps. So after this, the signal will be something like this. So we'll get the same signal, but when we get 5.4 like that, that will be rounded off to 5 only. And the last step is encoding, where each quantized level is given a binary code. So these are the quantized levels. For every binary or for every quantized level, a binary code like 1, 0, 1, and so on. So some kind of binary code will be given. These binary numbers are then combined together in order to form the digital data. So here we are getting 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 binary values in the form of zeros and ones. So if you combine all of them together, that is nothing but the digital data. So output here, it's a stream of ones and zeros that computers can store, send and process. And here you can see how the analog signal is converted into digital signal through techniques called sampling and quantization. So here in this image, you can see an analog signal which is a smooth continuous time sine wave, and amplitude changes smoothly over time. This is how natural signals like voice or music usually looks. And at the bottom you can see the same signal after sampling. Sampling is nothing but measuring the signal's amplitude at fixed intervals of time. So the same curve, it is represented in the form of fixed time intervals. Instead of smooth curve, you now have a series of individual points which are called as samples. This is still analog in amplitude but discrete in time. And here you'll see how the quantization and digitization were done. So this blue curve, it represents a sampled analog signal. This one, this is a sampled analog signal, still continuous in amplitude. Whereas all these red dots, they represent quantization, where each sample's amplitude is mapped to the nearest discrete level. These levels are fixed numbers, usually between 0 and 7, representing possible binary codes. And after quantization, signal becomes both discrete in time as well as discrete in amplitude, which gives you the digital signal. So, as I told you, if you get any rounded off values, say if you have some value or the height of the signal here in between 5 and 6, say 5.4, then it will be rounded off to 5 only. So you can see there are no decimal values after quantization.